Welcome to this video lesson. Today we will be looking at the 5 equations of motion for uniform acceleration. The learning goals for this particular videos include using the 5 physics equations for constant acceleration to solve physics problem which undergo horizontal motion. So we'll focus on horizontal motion today. Using answers to part of a question to come up with an appropriate question for it. So seeing an answer and building a question for it. Following a 5-step problem solving technique to solve physics problems, and that includes the 5 following steps. Pictorial view, or what we call a system diagram, physics representation, so any appropriate diagrams, word representation, which includes assumptions and or describing the motions and forces acting on the objects. The 4th step is mathematical representation, so solving something mathematically, and finally evaluation. So is the results reasonable, and how would removing some of the assumptions change the solution? And you can see that to solve a physics problem, we're looking at 5 different major steps, and only one of them involves mathematics. It is one of the bigger ones, but these previous steps and the next steps are also very important when we're solving physics questions. In the enhancement section of the last video, we saw that if we have a constant acceleration, we can use a velocity time graphs area and average slope in order to come up with 2 major equations. Those 2 equations, amongst with all these other equations here, only work when we have a uniform or constant acceleration, meaning that the acceleration is not changing throughout the whole interval or time interval. For the most part, when you start physics, the variables that you encounter a lot are the following: displacement, which is a change in position. We then introduce the change in time. We use position time graphs to come up with instantaneous velocities or average velocity. So in a lot of situations, you can have initial velocity and a final velocity. And then we have acceleration, which was the last things. So the average acceleration, for example, can be calculated by final velocity minus initial velocity, and dividing all of that by the change in time. So now let's say we have a physics problem, and in this physics problem we're given 3 pieces of information from these variables. So let's say we are given the displacement, let's say we are given the initial velocity, and let's say we are given an acceleration of an event. Using these 3 pieces of information, or any 3 pieces of information, we can use this table to find the other 2 informations. In this case, the missing variables are the final velocity and the change in time. So what we can do is, if we want to find the final velocity, then the only variable that's missing is the change in time. So we'll just go in this table, we looked at which one of these equations, which one of these 5 equations has the delta t missing. And we can see it's this one. We can see that this one has final velocity squared is equal to initial velocity squared plus 2 times average acceleration times the displacement. And we can just use this one because then we will put in the delta d, we will put the initial velocity, we would put the acceleration, and we can use those information to find the final velocity. If we wanted to find the change in time, then we have to use an equation, one of these 5 equations, which is missing the change in time, which is missing the final velocity. And that's this equation over here, which says the displacement is equal to initial velocity times the change in time, so that should say change in time, plus 1/2 of the average acceleration times delta t squared. And using this equation, we can just plug in the displacement, the initial velocity, and the acceleration, and use mathematics to find the missing variable, which in this case is the change in time. So this table, very useful. When you are given equation sheets, if you are given an equation sheet by your teacher, then usually it only has the formulas and it doesn't have all these missing information or what information you can find from it. So start getting used to just looking at the equations, looking for which variable is missing, and using that idea in order to find the appropriate equation to use for a specific question. We're going to do some examples a little bit later. And just to add in, I'm just going to put a delta in here as well, because both of these are not just t, they're the change in time. Let's talk about problem solving a little bit. We will use the following procedures to solve problems for our physics course. After reading the question, you are asked to complete a pictorial representation, physics representation, word representation, mathematical representation, and evaluation. The following example is a solved question and is adapted from Chris Meyer from 2014. So in a pictorial representation, what we usually do is we sketch, use coordinate system, we use labels to show us what information is given and what information is unknowns. We use symbols. Sometimes we need to do conversions, and sometimes we describe events. For me, most of the time, what's important is to sketch, make sure every thing that's given to you in terms of information is labeled. So that includes unknowns and knowns with proper symbols. In this equation, we can see that we have a runner. It says that at event 1, the runner is passing the 6th marker, and at event 2, they're passing the 8th marker. We know that position 1 is 60 meters in the positive x direction, and we know that position 2 is 80 meters in the positive x direction. And we can see that it says the velocity is 9.7 meters per second. This kind of implies that there is no change in velocity, and velocity throughout the whole interval is constant. And in this case, what we're trying to figure out is what is the change in time. This pictorial representation is sometimes referred to as system diagram and is the key to solving any physics problems. A lot of times we need to draw this out to kind of figure out what information we have, what information we don't have, and then go from there. In the next section, which is the physics representation, draw motion diagrams, motion graphs, velocity, vectors, events, and later on when we do force diagrams, also force diagrams as well. So in this case, kind of thinking about how to draw this out, we have a reference point somewhere in here, and basically our object is 60, or our runner is 60 meters away from it in the positive x direction. And we can see that if we were to draw a dot diagram or a motion diagram, we will see that the object is moving at a constant velocity. In this case, we're assuming that velocity 1 and velocity 2 are both in the same direction, and they're both moving in the positive x direction. We also draw some motion diagrams. This is where you are going to become experts in drawing motion diagrams. We can see that here we have a position time graph. We can see that since this is positive x, we're labeling this as x. And this is our velocity time graph, and velocity is positive when it's moving to the positive x direction and negative if it's negative. So we can see that in terms of position time graph, the position is changing. Initially it's 60, then it's 80, and it's going at a constant velocity, so we get this nice straight line. Since the slope of this line is always constant, velocity is also constant throughout. This is event 1, this is event 2. So this is when it's at the 6th marker, and this is when it's at the 8th. Once we have the motion diagram, we'll have a better understanding of what's happening. So then we are going to do is what's called a word representation. In this case, you are describing motion using no numbers, kind of explaining whys or hows and assumptions. So in this case, one thing you can say is that the runner travels in the positive direction along the track. We know that it's moving in this direction. That's the positive direction. We can see that from the position time graph as well. We assume she runs with constant velocity. This is a huge assumption because if these information are given to you and the v is given as 9.7, you don't actually know if it's the initial velocity or the final velocity. In this case, we're going to make an assumption that is constant throughout. And we're going to assume that there's no air resistance. So we're assuming that air is neither pushing her forward or resisting her motion. So these are some of the assumptions that we're making. One very common assumption that we make in many of our physics problems is that there's no air resistance. So this is almost always here. And later on when we're doing our evaluation, sometimes we have to think about what would have happened if she was not running at a constant velocity, or if air resistance was negligible, or was not negligible. Then after all of this, we're going to do a mathematical representation. I'm going to leave it here. So describe steps, complete equations algebraically, isolate substitution with units, and final statement. So in this case, we want to find the displacement. And I will write that as delta D is the information that we want to find. Maybe I'll bring this down a little bit so we have the system diagram in as well. And we want to solve for the change in time. So we want to figure out what the change in time is. Well, in this case, we don't have to use our 5 equations yet. We can kind of start using it, but basically we have our average velocity is given to us, and the average velocity between events 1 and 2, maybe I'll just change this and write it as between events 1 and 2 is equal to the displacement from 1 to 2 divided by the change in time from 1 to 2. Well, these are all great. We're looking for the change in time, so we have to do some rearranging. So I'm going to take the reciprocal of both sides and then multiply both sides by the displacement. You can multiply both sides by delta t and then divide by this. There's many different ways of doing it, or you can use the crisscross method of just changing these two. So once we rearrange it though, we are going to have delta t from 1 to 2 is equal to the change in displacement from 1 to 2 divided by the average velocity between 1 to 2. Now I'm going to take everything to be positive in the positive x direction here, and therefore I know that the change in position is going to be position 2 minus position 1. That's 80 minus 60. So I can either write it out, well, let's write it out, 80 minus 60 divided by the average velocity, which is 9.7. When I do all of this on my calculator, I will get an answer of 2.061855, and it keeps continuing. But basically, based on my numbers, I have one significant figure in my positions, and if I'm subtracting them, I still have one significant figure, and when I divide it, I still have one significant figure. So my final answer should be rounded to 2. And basically my unit here is in seconds, and that is my final answer. I often box my final answer, or sometimes I highlight it, and it takes approximately 2 seconds for this runner to be running a distance of 20 meters with an average velocity of 9.7. Does it make sense? Well, if the average velocity is about 10 and the person is running 20 meters, then it should take 2 seconds, so that kind of makes sense. So let's look at the evaluation of the answer now. So when you're doing an evaluation, you got to kind of talk about does the answer have a reasonable size, direction, and units? Why? What if your assumptions did not exist? How would that change the answer? So in this particular case, this a small interval of time is reasonable because she is traveling a very short distance, only 20 meters. Time does not have a direction. So that makes sense. There's no direction here. The units are in seconds, which are also reasonable for that short interval of time. Air resistance, if it was going against her, would be slowing her down and increasing that time interval. If the air resistance was going in her if the air was moving in the same direction as she was, it could, depending on its relative velocity, could actually speed her up as well. So now, given the answer above, write down an appropriate question for this solution. This is a very good practice to do for students because a lot of times students are encountered with the questions and they try answering, but thinking backwards is a very important skill. I'm just going to zoom out a little bit here and kind of put everything into perspective and kind of especially look at the pictorial representation to start developing a question. So in this question, we have the runner who is running. So we have a runner, and the runner is passing through the 6th marker and the 8th marker. So we know that much from just the beginning of the picture. So the runner runs and passes through markers 6 and 8. The position of marker 6 and 8 are, in this case, position of marker 6 is 60 meters, and for 8 it is 80 meters in the positive x direction relative to, in this case, it's the reference point. We're going to call it the starting point. Okay, now looking at the diagram, I've put down this set of information, this set of information. Now we know that we're going to say, assuming that the runner is moving at an average velocity, or a constant velocity in this case, of 9.7 meters per second, we want to determine the time she spends between markers 6 and 8. So let's see if we have used all the information. So 6th and 8th marker, they're in there, their positions are there. We have the average velocity included, that's in the 9.7 meters per second, and we're trying to find the change in time between these two events over here. They're included, so this is looking fantastic. So the question has all of the information. And this is how we develop a question, actually just looking at the pictorial representation. In this case, I also looked at the assumption as well and used some of that idea in there as well. But you should be able to just look at a pictorial representation and come up with a question, or look at a question and draw the pictorial representation. This is always the very first step and probably one of the most important ones when you're doing the question. I'm also a huge fan of physics representation, so you should get really good at it throughout this course. Let's go through a couple of examples and just to get an idea about kind of drawing things out, going through the 5 steps process, and finally just how to use the equations to solve these types of questions, because the last questions just use a general average velocity equation, but sometimes we have to use more, one of the 5, and that's what we're going to do in this question. So in this particular question, we get an automobile safety laboratory which performs a crash test of vehicles to ensure their safety in high-speed collisions. So this first kind of sentence here is giving us some information, but it doesn't have any key information yet. The engineers set up a head-on crash test for a smart car which collides with a solid barrier. Okay. The engineers know that the car initially travels at 100 kilometers per hour. I am going to highlight this set of information. This is what the speed is initially. Then the car, when it crashes, crumples for 0.78 meters, and this is during the collision. Then the engineers have a couple of questions. First of all, how much time does the collision take, and what is the car's acceleration during the collision? So we've highlighted the most important informations in this question so far. There's some stuff that we might need to interpret from the question, but let's start drawing it out to kind of get a better idea. We have a testing facility, and in this facility we have a car which is moving, and instead of a car I'm just going to use a cart, and this cart is moving at speed, let's call it initial velocity, in this direction. The car is going to go, it's going to hit a wall, and it's going to reach the wall here. And at this position also, actually I'm going to start numbering these. Instead of initial, I'm going to use V1 here. And then right here, its speed is still the same. I'm going to call this event number 2. So in this case, it is V2. And then it is going to crumble. So this is hard to draw, so I'm going to draw another line to kind of show what happens in the third diagram. So it crumples a little bit, and the car has now moved a little bit. And there's a change in here. So this is event 3, this is event 2, and this is velocity 3. And there's a little bit of a displacement here, and that displacement is the displacement from event 2 to event 3. So I'm going to label that there. What other information so do we have? We can start putting some values in. So first of all, initial velocity is given to us at 100 kilometers per hour. And I'm going to change that right away into meters per second, because we can notice that here the amount of displacement that's given to us is in meters. When a car collides, the collisions are usually not that long, so we don't want to start measuring things in hours. So how do we make that conversion? Well, we got 100 kilometers per hour. We know that in every hour, there is a certain number of seconds. So 1 hour is 3,600 seconds. And we know that in every kilometers, there is a certain number of meters. So in 1 kilometer, there's 1,000 meters. Why did we place things the way we did? Well, kilometer needs to become meters. And by putting it like this, these kilometers cancel. And hour needs to become seconds. So by putting it in this method, we get rid of the hours. Now, when we do this on our calculator, we end up getting 27.7 repeated meters per second. I'm going to leave the answer like this. This is not my very final answer, so I will have to do some rounding here and there. So at the very end, but I'm going to keep this value as 27.7 meters per second. Okay, so I have my initial velocity. So we know that V1 here is 27.7 meters per second. And my units, I'm going to use just the fundamental units. So I'm going to just write it as, I write it as meters per second. And the direction is given to me based on my vector here, this one over here. So I'm not going to actually show the direction there. Velocity 2 is also going in that direction. So basically, this vehicle is going at the same speed, just before it touches the wall, it is still going at the same speed. So I'm going to label this also as 27.7. Now, the car starts to crumple for a displacement. So this displacement is 0.78 meters. I'll write that information down. And it's going to crumple, and at the end, it's not going to be moving anymore. So my final velocity here, something that's not mentioned in the question, but something that's the question implies, is that at the very end here, the speed of the car is going to be 0 meters per second. So I have I have a lot of information now. In fact, I have the velocity before, velocity after, and the displacement. And as I said in the beginning, whenever we have three information, we can find the other informations from the question. But before we start anything in terms of math, I'm actually going to label this as part A. This is the first step of solving the question. Then we're going to go to part B, which is the physics representation of the question. So I'm going to draw a motion diagram. And in this motion diagram, I'm going to assume it doesn't really matter where the starting position is. I'm going to assume that the starting position is right when the car starts moving. Or sorry, not when it starts moving, but let's say somewhere along the line where it's moving. So it moves at a constant velocity. So I'm going to have it go at a constant velocity so the dot spacings are all the same. And at some point it starts to crumble and the spacing between the dots get closer and closer to each other. So this is event 1. This is when the car is just starting to move. It moves, and then right at this section over here, it starts to hit the wall and it starts to slow down. So this is event 2. This is the start of the collision, and this is the end of the collision when the car stops moving. So I have 3 events here. And really, in terms of figuring out how much time does the collision take and what is the car's acceleration during the collision, I don't really care about anything between events 1 to 2. That's not part of the collision. Part of the collision is only from event 2 to 3. So this is the interval that I really care about. Now, so the events that I really care about, I'll highlight. Those are events 2 and 3. I'm also going to draw some the position time, velocity time, and acceleration time graph for these. So I'm going to move this up a little bit. I have all the information already in my pictorial view. I don't even need it anymore. Actually, one thing I should add to it is that we're trying to find the acceleration between event 2 to 3. And we're also trying to figure out what is the time it takes for the collision. So these are kind of the information that we need. Now we're going to have position time, velocity time, and acceleration time for this question. And I'm going to label this as dv and acceleration. I'm not going to include units in this one just because I'm just sketching. I do need a direction here. I've missed that one. In this case, we're not given any information, so we get to choose kind of any sign convention. You can do positive x, you can do positive east. It's completely up to you. So I'm going to imagine that everything is moving in the positive east direction here. And so positive for me will be anything that's going in the east direction, and if anything is going in the west direction, then it would be negative east. How does my I'll draw my velocity first. Actually, my velocity kind of starts at 100 kilometer. It goes straight, 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 and then from event, this is event 1, event 2, and from event 2 to 3, the velocity drops to 0. That's my velocity time graph. In terms of my position time graph, my position is initially here. Let's say it's at the reference point. It increases at a constant rate, and then it starts to slow down and kind of reach 0. So how does that look like? So initially the values are high in terms of speed, so the slope is also going to be pretty high. So it's going to kind of go like this all the way to event 2. And then from event 2 to 3, the slope of my line, you can see this is the slope value. Let's say it's about 100 kilometers per hour, so that's my slope. Let's say this is pretty steep. And then the steepness, which is represented by the value of velocity, we go from 100 to 0. So all of a sudden the slope changes from 100 to 0 right at point 3. So at point 3, my slope is 0. So if I were to draw out my position time graph, it kind of is constant, 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 and it reaches a 0 at time 3 or event 3. Now I have my position time graph, acceleration time graph. Acceleration right here, acceleration can be found by the instantaneous rate of change of velocity time graph. That's the slope of a tangent, slope 0, 0, 0, 0, all the way to event 2. So I'll just draw some dashed lines kind of indicating where all the events are. So acceleration is 0 all the way here. And then you can see that the acceleration here, we got a very steep slope, and the slope is negative. So in terms of the value here, we're going to have a negative slope, and the slope is kind of constant. You can see that the slope doesn't change. So slope of constant here is all throughout from event 2 to 3. It's a very steep line, so the value is large and it's negative, so it's in the negative region. Does this make sense in terms of objects slowing down or speeding up? So between event 2 to 3, which is our collision, and I will label this actually, this is 1, 2, and 3. We said previously if the velocity and acceleration have opposite signs, and in this case they do, velocity is positive and acceleration is negative, then the object is slowing down during those events. in this case, the object is slowing down, so that does make sense. So that is part of the evaluation later. The third part of doing these questions is the word representation. So kind of like, are we making any assumptions or kind of explaining the situation? So in terms of explaining the situation, we can say that from 1 to 2, constant velocity, and then from 2 to 3, object, or in this case, the car moves east. Here it also moves east, and then it slows down to 0 velocity, and that's it actually. And we can talk about acceleration, but we can also actually make a few assumptions in here. So we are assuming that acceleration is constant, and that and no air resistance. Now, there's good reasons why there's no air resistance during the collision itself. Even if there is an amount of air resistance, is negligible compared to the acceleration of the car, or how much push there is from the wall. But outside of that, when we're looking at one huge big assumption here is the acceleration is constant. Um, we can't really imagine that when the car collides, the acceleration is exactly constant throughout the whole event. So this is actually a huge, huge, huge assumption in this particular question. Okay, we have a good amount of information. Now we need to solve it just so that we can kind of do everything in actually, maybe we can't do everything in the same page. So I'm going to actually move things a little bit. I'm going to move it up to here. The reason why I'm moving it up to here is because we only care about events 2 and 3, and all of the information is here. We are going to go to the mathematical section of this. I'm going to load up my equations here so it can kind of guide you into which equations you have to use to solve this. So let's call this again section D. And here's how we use our math skills to solve this type of question. So in this case, we have 3 pieces of information. We have velocity 2, velocity 3, and the displacement between those 2 points. In these set of equations, you can see initial and final. So in this case, our initial is 2 and our final is 3. The information that we have are, again, the information that we don't have, and we're trying to find our acceleration and change in time. Let's first find the acceleration. And to find the acceleration, I need to find an equation that doesn't have the change in time in it. This equation has change in time, this equation has change in time, this equation has change in time. This equation does not have the change in time, and that's what I'm going to use first to find my acceleration. I'm going to write out the equation, and the equation is final velocity. Instead of final, I'm going to use 3, and it's going to equal to initial, that's going to be 2, plus 2 times the acceleration multiplied by the displacement from 2 to 3. And the acceleration is also from 2 to 3, and these are all vector quantities. I am going to, I've labeled this before, but I'm going to take my positive to be in the east direction, and I'm going to make sure this is nice and clear in the question, or in my solution. The velocity 3 is 0 meters per second. I am going to use that value here. So that's 0 squared is equal to velocity 2 is 27.77777. I forgot the repeated. And it's going in this direction. That's same as my positive, so I'm going to use a positive value here. This is going to be 27.7 repeated squared plus 2. The acceleration is what I'm trying to find, so I'm just going to leave it as A. For my displacement, my cart is displacing from 2 to 3 in the right direction. Since it's displacing to the right and my right is also my positive, I'm going to use a positive value here of 0.78. Once I have this, I'm going to rearrange it to find my acceleration. So I'm going to subtract both sides by 27.7 squared. And that's going to be 2a times 0.78. And if I want to find acceleration, I will divide both sides. So this is going to be negative 27.7 squared divided by, sorry, the negative is not inside the brackets, and we got to be very careful with this. Good, negative 0 minus that, I'll just write the 0, that's okay, and then divided by 2 times 0.78. I'm going to put that on my calculator, and I am going to get negative 491.85 meters. The unit for acceleration is meters per second squared. I'll just write it like this. And since my positive direction was in the east, I'm going to write this as east. And this is kind of saying that the object is accelerating in the negative direction. And if I zoom out and look at my graph, I can see that that's correct. It is actually accelerating in the negative direction. So this actually makes sense. My answer is only good to one significant figure because of the 100 kilometers per hour. So I'm going to estimate this. Actually, let's zoom in a little bit. I'm going to estimate this as negative 500 meters per second squared in the east direction. And now I have my first part of the question, which is what is the acceleration? Let's find the change in time as well. So I'll zoom out a little bit more so that we have a little bit more space. For part B, I'm going to say this is part A, for instance, and this is part B. I'm trying to find an equation which doesn't have acceleration in, so I can find the change in time. That equation is right here. This equation has the displacement, initial velocity, final velocity, and time in it. Let's do it. I'm going to plug in all my values. We got displacement is equal to the initial velocity plus the final velocity. In this case, displacement is from 2 to 3. Velocity 2 plus velocity 3 times the change in time from 2 to 3 divided by 2. Let's rearrange the equation. Actually, we can either plug in the values right away or rearrange first. It doesn't really matter. In this example, I'll rearrange. Delta t from 2 to 3 will equal to 2 times the displacement from 2 to 3 divided by the velocities added together. Now I will plug in all the values. So 2. I'm still using this positive east convention. So my displacement is to the right, same as east direction. So that's going to be a positive 0.78. My velocity, initial velocity is 27.7 repeated, plus my velocity 3, which is 0. And when I do this on my calculator, I get an approximate value of 0.06 approximately meters per second squared. And that's it. So these are, and actually, no, that's not it. But this is kind of the time it takes for the collision to happen. Does it make sense? Well, actually, it's pretty reasonable because collisions happen in a very, very short amount of time. And this is not a really bad estimation. So in terms of our final part of the answering these types of questions, so let's say in part E, isn't reasonable because the time interval is small, and this is small for collisions, and acceleration was negative and velocity was positive, meaning that it slows down, and that's exactly what happened. The high acceleration also makes sense because it needs to accelerate really fast during the collision. And we can talk more about this as well, but usually sometimes I ask you particular questions about the evaluation, and sometimes you just need to kind of look at it and see if it's reasonable. Let's pause here for now. I think this question had a lot of content in it, a lot of good information in it. So try looking over it again, kind of analyze it. If you have any questions, make sure you ask me. But in terms of tomorrow, we'll do a little bit more examples on these types of questions, and we'll practice drawing the proper diagrams, talk about proper assumptions, and using proper equations to solve the problems. Have a wonderful day.